Hello there, and welcome to Science for Sleep. Winter is a season that reshapes the planet in quiet, unnoticed ways, a stretch of time when the ordinary becomes quietly extraordinary, and the familiar world takes on a soft, dreamlike transformation that invites anyone watching to slow down and drift into a gentler rhythm. As the air cools and the light thins, the landscape becomes a place where physics, biology, and natural cycles reveal parts of themselves normally hidden beneath the busier warmth of other seasons. In winter, stillness has its own language, carrying tiny messages in frost patterns, in drifting snowflakes, in the crisp echo of footsteps across a frozen field, and in the way distant hills seem to float when cold air bends the light. It is a time when forces that are usually drowned out by heat or motion begin to speak more clearly. Beneath a surface of quiet, the planet is alive with processes both subtle and surprising. Snowfalls are not merely showers of frozen water but intricate collections of crystals forming around microscopic specks that might have begun their journey millions of years ago in the tail of a comet or in the debris of a shattered asteroid. As these crystals drift downward, they gather water vapor that freezes into branching shapes, trapping cosmic dust, glassy droplets, and strange minerals inside, creating tiny time capsules of the solar system's history. When scientists melt snow collected from remote places, they sometimes find these extraterrestrial grains glimmering like specks of stardust, silent travelers that crossed immense distances before being caught by Earth's winter breath. The quiet world of winter also carries sounds that belong only to cold weather. On the coldest mornings, footsteps in powdery snow produce a sharp, squeaking crunch caused by tiny ice grains fracturing under pressure. Lakes locked under ice send out low, resonant booms that ripple through the frozen surface like whale songs. Temperature changes make the ice expand and contract, producing cracks that shoot across the surface in long, echoing lines. Even thin sheets of ice on puddles can shatter into high, chime-like tones if stepped on just right. In extremely cold, still air, distant noises travel farther and clearer because sound waves bend through layers of dense air near the ground, creating an acoustic landscape that feels sharper and more alive than the muffled quiet of warmer seasons. Winter also reshapes water in unexpected ways. Rivers can briefly reverse direction when ice jams block their usual flow or when strong, persistent winds push water inland across wide river mouths. For a moment, currents may seem to defy gravity, sliding backward until the jam breaks or the wind calms. The atmosphere itself becomes a layered structure during the coldest nights. Dense air settles close to the ground while warmer air rests above, forming an inversion that traps pollutants, moisture, and chemical reactions near the surface. The air we breathe during a deep winter night can be chemically different from the air we inhale on a mild afternoon, filled with altered mixtures of nitrogen oxides, particulates, and organic vapors that behave differently in the concentrated cold. Winter storms, especially those near large lakes or coastal regions, can generate lightning within swirling snow, an event called thundersnow. Inside these storms, ice crystals and soft hail called graupel collide in turbulent updrafts, exchanging charges until electric potential builds enough to burst into lightning. The flashes glow differently from summer lightning, scattering softly through snowflakes and clouds to create eerie bursts of diffuse light that illuminate the storm like a camera flash inside a fog. Light behaves differently across winter landscapes too. Fresh snow reflects most sunlight, turning open fields into luminous plains that cool the air above them and change how shadows fall. Temperature gradients near cold ground can bend light so that distant objects shimmer or appear lifted, creating distortions called superior mirages. Ice crystals drifting through the air act like tiny prisms, producing halos, sundogs, light pillars, and veils of brightness. At night, the glow of cities can travel farther across snow-covered land, lighting the sky with soft illumination that never appears during warmer months. Winter reveals hidden physics, slowing molecular motion until forces that normally go unnoticed begin to influence matter in visible ways. Liquids thicken, gases lose energy, and some metals enter states where electrical resistance nearly vanishes, creating superconducting pathways for electrons. Magnetic properties of materials shift as thermal motion settles into stillness. Even biological systems behave differently, with plants entering dormancy that involves intricate chemical changes, animals adjusting metabolism to conserve energy, and insects producing natural antifreeze compounds that keep their cells from freezing solid. Beneath frozen lakes, fish move more slowly in cold, dense water that holds oxygen differently, creating a world that is quiet but thriving beneath a thick layer of ice. Soil under snow undergoes processes invisible to anyone standing above. Microbes continue working in the thin liquid films between soil particles, breaking down organic material at a pace governed by cold chemistry. Roots of trees and shrubs remain alive, sending slow signals and storing nutrients for spring. In deep winter forests, snow muffles sound so thoroughly that even a falling branch lands with a soft, padded thud. Snow acts as insulation, trapping heat in burrows where small animals sleep or rest through the frost. Each snowflake that falls, unique in shape yet formed by the same simple rules of physics, is a tiny sculpture shaped by humidity, temperature, and pressure changes during its journey downward. Sometimes snowflakes grow into elaborate, feathery dendrites. Other times, they form simple plates or needles depending on conditions. This constant variation turns winter storms into galleries of transient art, each crystal existing for only a moment before joining the white expanse. Deep cold also transforms water surfaces into patterns that look like artwork. When lakes begin to freeze, long lines of tension and compression form across the surface, creating cracks that spread like lightning bolts. In shallow areas, ice may grow in circular formations, each ring caused by temperature differences and subtle currents below. In some rare cases, rivers form ice disks, slowly spinning circles of ice created by rotational eddies. Frost creeping across windows forms fractal patterns shaped by tiny impurities in the glass, by indoor humidity, and by the angle at which cold air brushes the surface. These frost ferns resemble frozen forests, branching and fracturing in ways that mimic the mathematics of growth found in coral, tree branches, and lightning. Even human breath behaves differently in winter. Moisture condenses instantly, forming visible clouds that swirl and diffuse based on tiny air currents around the body, revealing the otherwise invisible turbulence we carry with us. As temperatures drop further, even this breath can crystallize on scarves, forming thin layers of frost. The scent of winter is different too. Colder air carries fewer volatile molecules, making smells less intense and less concentrated by temperature inversions or nearby sources. Forests smell sharper, cleaner, and more metallic because resins and plant chemicals evaporate differently in the cold. Winter nights are among the quietest times on Earth. Snow absorbs sound, cold air suppresses biological activity, and long nights create prolonged darkness that feels deeper than any other season. Yet, in this quiet, life continues in hidden ways. Owls hunt silently over snowfields, using hearing so precise that they can detect the faint rustle of a mouse tunneling beneath the snow. Wolves leave long trails of prints across frozen ground, their breath visible in silver puffs. Trees creak as sap inside them contracts and expands, sometimes cracking their bark in loud pops known as frost cracks. Clouds of breath from animals gather and vanish into the cold, tiny reminders of warmth in an otherwise icy landscape. Under the snow, small mammals build networks of tunnels in a world called the subnivean zone. This insulated space stays much warmer than the air above and protects them from predators and wind. When the sun returns after weeks of dim light, winter landscapes respond dramatically. Ice crystals sparkle, the low sun casts long shadows across snowdrifts, and even simple fields become striking scenes painted in pale blues and bright whites. Winter also offers rare atmospheric phenomena. In polar regions, where temperatures plunge even lower, ice crystals in the upper atmosphere can create arcs, circles, and complex halo displays around the sun or moon. Light pillars rise like ghostly beams from streetlights. Sometimes clouds form with iridescent colors when tiny ice crystals diffract light into shimmering pastel shades. During extremely cold nights, moisture in the air can freeze into suspended particles called diamond dust, creating a world that sparkles as though filled with floating stars. Even our sense of time behaves differently in winter. Long nights and slow processes make hours feel stretched, while the muted environment invites introspection and rest. Winter's quietness encourages a different form of attention, one that notices the delicate sheen of hoarfrost on a fence rail, the way snowflakes settle on eyelashes, or the rhythmic crunch of boots across a frozen path. Every transformation the season brings, from reverse rivers to cosmic dust and snowflakes, from thunder and blizzards to halos around the sun, reminds us that winter is not simply cold weather but a shift in the entire behavior of the natural world. It is a time when the planet's deeper workings become faintly visible, when slow forces rise to the surface, and when the world pauses just long enough for us to glimpse the quiet, beautiful complexity woven into the fabric of Earth. Winter, in all its stillness and quiet mystery, invites us into a world where the ordinary rules of nature appear to soften, slow, or shift into unfamiliar forms, and even simple materials reveal hidden dimensions of themselves once the temperature drops far enough, as though the cold unlocks secret chapters of physics, biology, and atmospheric behavior that remain sealed during warmer seasons. And even the most familiar elements, air, water, soil, and light, begin to act in ways that seem subtle at first but become astonishing upon closer attention. For instance, water alone demonstrates an entire gallery of unusual behaviors, forming different kinds of ice with distinct crystal structures, varied strengths, and unique mechanical properties, a reminder that winter is not merely a visual transformation but a deep physical reorganization of the environment, one that quietly rewrites the conditions under which matter behaves. For scientists, winter is a vast outdoor laboratory that costs nothing to operate yet offers extreme conditions that would otherwise demand sophisticated equipment, and for the rest of us, it is a soft-spoken reminder that our familiar world still contains hidden behaviors that appear only when the planet lowers its thermostat far enough, revealing details that sunlight, warmth, and motion obscure the rest of the year. Some regions even experience snow that forms without passing through a single cloud. On the coldest and calmest days, tiny ice crystals materialize in open air, shimmering like suspended diamonds in direct sunlight, despite the sky being a perfect, uninterrupted blue. This natural wonder, often referred to as diamond dust, arises when the air near the ground is both extremely cold and extremely still, yet contains just enough water vapor for crystals to assemble directly from the gas phase without ever entering a cloud, forming delicate plates or needles that drift downward so slowly that the world seems filled with a silent, floating glitter. At night, streetlights turn these crystals into towering pillars of light or glowing halos, transforming quiet neighborhoods into something dreamlike. Even the slightest disturbance, footsteps, the movement of a car, the push of warm air from a chimney, can scatter or reshape these tiny crystals, making diamond dust a form of precipitation that blurs the line between weather and optical phenomenon, a delicate dance between temperature, humidity, and stillness that only winter can choreograph. The cold can also transform the very color of the sky in ways that no other season achieves. When the sun sits low on the horizon during deep winter, its light travels through a thicker slice of atmosphere before it reaches the eye, encountering more air molecules, more tiny suspended particles, and often more ice crystals high in the sky. These interactions scatter shorter wavelengths, blues and violets, much more efficiently than longer ones, leaving behind a canvas of soft reds, warm oranges, and glowing pinks at sunrise and sunset. Because cold air holds less moisture than warm air, the winter atmosphere typically displays better clarity, removing the haziness that often mutes summer skies and allowing twilight colors to appear more saturated, with deeper blues arching overhead and richer gradients of crimson and gold lingering near the horizon. In polar regions, where the sun barely rises or sets for weeks, this effect stretches into extremely long dawn-like or dusk-like glows that can paint the sky for hours. High-altitude ice crystals further refract and reflect this tinted light into arcs, pillars, halos, and subtle colored glows rarely seen during warmer seasons, making winter not merely a change in temperature but a transformation of the sky's palette itself. Freezing air can change how ordinary materials behave so dramatically that they begin to resemble entirely different substances. Rubber that bends with ease in summer may turn stiff, rigid, and brittle in deep cold, snapping sharply instead of stretching. Plastics that normally resist impact may suddenly fracture under loads they would easily withstand in warmth. Metals contract enough to alter the way gears mesh, joints fit, or hinges rotate, and these shifts can tighten mechanical systems, change tolerances, and create stresses that engineers must anticipate when designing equipment for cold climates. Oils thicken, slowing bearings and gears that normally spin freely, and even everyday materials like glass become more vulnerable to thermal shock if one part warms or cools much faster than another. On a microscopic level, cold reduces the thermal motion inside solids, making atomic lattices less forgiving when objects are bent, struck, or forced to deform. Engineers and architects must consider all of this when selecting materials and designing machines, because winter demonstrates vividly that the properties of a substance are not fixed traits, but responses shaped by environmental conditions. Snow itself can form under surprisingly clear skies, appearing when tiny ice crystals develop in extremely cold, dry, and stable air without the need for towering clouds. These delicate particles drift downward gently, sometimes lingering in the air for long periods, sparkling in sunlight or glowing under street lamps at night. Because they are so small and light, they rarely accumulate deeply and can be disturbed by the softest breath of wind. Such snowfall, found in polar regions, high-altitude plateaus, and broad open plains, proves that precipitation need not arise from dramatic storm systems. It can emerge quietly from the lower layers of the atmosphere when conditions become calm, cold, and clean enough for ice to assemble directly from vapor. Winter winds can also behave differently, carrying particles much higher into the atmosphere than similar winds during warmer seasons. When intense cold sweeps across open landscapes, strong pressure gradients develop that encourage pockets of powerful upward motion. Fine snow crystals can be lifted off the ground and injected into fast-moving layers above, traveling great distances before settling. Even small particles like dust, salt, and plant fragments can hitch a ride on these uplift currents, reaching altitudes typically associated with more violent summer storms. Scientists use this property of winter air to study the movement of nutrients and minerals across continents, tracing how cold season winds transport environmental signatures of soil, vegetation, and sea spray over long distances. The combination of strong lifting forces, low humidity, and lightweight particles turns winter into an efficient transporter of atmospheric material. Animals, too, undergo transformations so profound that they appear almost like altered versions of themselves, optimized not for warmth but for survival in extreme cold. Mammals grow thicker fur, but the changes run deeper. Many shift their metabolic pathways to burn stored fats slowly and efficiently, conserving precious energy during times of scarce food. Some creatures reduce their heart rates dramatically, lowering oxygen demand so far that their bodies slip into a different mode of functioning entirely. Certain amphibians can even tolerate ice forming inside their bodies by controlling where freezing occurs and producing protective chemicals that prevent cellular damage. Birds remodel internal organs throughout the season, enlarging digestive systems when food requires more processing or shrinking them to lighten the body during long migrations. These transformations reveal that biology is astonishingly adaptable, reshaping itself from the inside out when the environment demands it, and winter becomes a time when the full creativity of evolution is on display. Even lakes transform deeply beneath their frozen surfaces. As winter arrives, the surface waters cool until they reach the temperature at which water is densest, causing them to sink and form stable layers beneath slightly warmer water, which floats above. Once the lake's surface freezes, this entire structure becomes locked in place, creating a stratified system where layers do not mix for months. Light can still penetrate clear ice, allowing microorganisms in the upper layer to continue photosynthesis, while deeper zones remain locked in darkness. Nutrients released from bottom sediments accumulate slowly, and oxygen cannot easily reach lower waters, creating steep chemical differences between layers only a few meters apart. When spring eventually melts the ice, the lake undergoes a dramatic mixing event, redistributing nutrients, carbon dioxide, and trapped gases throughout the water column, an event that shapes the lake's ecology for the rest of the year. Winter thus turns lakes into miniature oceans with internal seasons and stratified worlds. Even solid ground moves in winter in ways that seem impossible. Freezing soil can rise upward with enough strength to shift, crack, or lift heavy structures. This phenomenon, called frost heave, begins when moisture within the ground migrates toward freezing fronts. As water turns to ice, it expands and forms pockets or lenses of ice that push the surrounding soil upward. Over time, this expansion can lift roadways, tilt fences, crack foundations, or disrupt pipelines, making frost heave a major engineering challenge in cold climates. Winter soils behave like living, shifting systems, pumping moisture upward and transforming frozen landscapes with quiet but powerful movements. All of these winter phenomena, diamond dust glittering in clear air, skies painted in deep cold colors, materials reshaping their properties, animals transforming their bodies, lakes developing layered internal worlds, and soils rising with hidden force, remind us that winter is not merely a temperature on a calendar but a complete reorganization of physics, chemistry, and biology. It is a time when the world slows enough for its deeper workings to show through, offering glimpses of processes too subtle to notice during warmer, faster seasons. For those who look closely, winter reveals not emptiness but transformation, not silence but the soft hum of hidden activity, and not dormancy but the quiet, intricate labor of a world reshaping itself under the gentle weight of cold. The process continues as more water is drawn in, feeding additional growth, and over time these icy formations can heave the surface by several centimeters while exerting significant upward pressure that affects everything resting above them. Buildings, roads, and fences can shift, tilt, or even crack in response to these forces, especially in regions where repeated freeze-thaw cycles occur and the upper soil layers fluctuate around the freezing point with remarkable sensitivity. Different soil types respond in different ways. Clays and silts, which hold more water, experience larger changes in volume, while sandier soils, though less prone to extreme heaving, can still rise under the right combination of conditions. Engineers plan for these forces by designing foundations that extend below the deepest expected freeze line or by using materials capable of tolerating movement without fracturing. For people observing the ground in winter, frost heave is a quiet reminder that the surface is not fixed or stable. Instead, it is a dynamic, shifting layer that reacts dramatically to temperature, moisture, and structure. Above this restless ground, winter may appear to shut down entire ecosystems as plants stop growing, insects disappear from sight, and many animals retreat into hidden shelters, yet the soil beneath the snow remains surprisingly active. A thick blanket of snow acts as a natural insulating layer, trapping heat from the ground and preventing sudden swings in temperature, creating a protected zone where microorganisms continue breaking down organic matter and releasing nutrients that plants will depend on when spring awakens the landscape. Small burrowing mammals carve intricate tunnel systems beneath the snow, searching for seeds, roots, and even one another in a secret world invisible from the surface, while fungi continue decomposing leaf litter and fallen wood, slowly recycling material that sustains the forest floor. In frozen streams, aquatic insects remain active beneath the ice, feeding, growing, and waiting for warmer water to return, and even plant roots continue tiny chemical exchanges with soil microbes. The visible landscape may seem still, but beneath the surface, a quiet engine of life continues turning, dividing the ecosystem into two contrasting layers, one frozen in appearance, and the other maintaining the momentum that drives the landscape into the next season. Snow crystals themselves grow into dozens of shapes depending on microscopic temperature changes. The structure of each crystal depends on the precise relationship between temperature and humidity as it forms within the atmosphere. Plates, needles, hollow columns, dendrites, and countless branching patterns emerge from slight shifts in environmental conditions. When the air is slightly warmer, crystals may grow broad and flat. When the air is colder, they stretch into long, slender forms. Small fluctuations in humidity influence how quickly different facets grow, shaping the symmetry and complexity of each crystal. Because the atmosphere is never perfectly uniform, a single snowfall contains countless variations, and scientists study these structures to learn about atmospheric conditions since each crystal stores a record of the environment in which it formed. Even within one snowflake, different sections can grow under slightly different conditions as it tumbles through shifting layers of air, resulting in a collection of tiny sculptures shaped by physics, each formed through a chain of microscopic events that will never repeat exactly. Snow becomes a gallery of natural design built one molecule at a time. Freezing fog can create ice coatings that grow thicker than the fog itself. This occurs when supercooled water droplets hover in stable air and cling to any surface they encounter. When these droplets touch tree branches, power lines, fences, or even the smallest protruding objects, they freeze instantly and add a thin layer of ice. As the fog continues to drift past, more droplets collect and freeze, creating a buildup known as rime. Because the process can continue for hours, the resulting ice can grow surprisingly thick despite the fog containing very little total moisture. Accumulated rime often forms delicate, feathery structures that extend outward in the direction of the wind, sometimes developing into elaborate, almost handcrafted-looking patterns formed entirely by atmospheric conditions. Unlike the clear ice formed by freezing rain, rime ice is porous and structured, making it lighter but still capable of weighing down branches and cables. Regions with persistent winter fog can awaken to landscapes coated in pale, spiky growths, highlighting how persistent small droplets can reshape environments when temperatures fall below freezing. Winter cold also reveals thermal patterns across the planet that even satellites struggle to detect. When the ground cools rapidly under clear night skies, different surfaces release heat at different rates. Rocks, soil, vegetation, and built structures each respond uniquely. These variations create a patchwork of temperatures that can only be observed when everything is exposed to the same intense chill. Researchers use winter conditions to study heat retention, moisture content, and material properties across large areas, since the contrast between warm and cold surfaces becomes more pronounced in winter than at any other time of year. The thermal signatures revealed by winter nights show how landscapes absorb sunlight, how cities trap warmth, and how ecosystems manage energy under harsh conditions. Even wildlife patterns can be inferred because animals leave subtle thermal footprints on the ground. Winter becomes a diagnostic season, revealing differences that remain invisible when the environment is warm and uniform. The quiet clarity of extreme cold acts like a spotlight, exposing hidden structures in the world. Some insects avoid winter death by removing water from their bodies through a strategy known as freeze avoidance, which reduces the amount of liquid that could turn into damaging ice. As temperatures fall, certain insects convert internal substances into forms that draw water out of their cells, preventing ice crystals from forming. By reducing their internal water content and producing compounds that lower their freezing point, these insects can survive temperatures that would destroy most living tissue. During deep winter, their bodies enter a state of profound stillness. Heart rates slow, metabolic activity drops to minimal levels, and movement ceases entirely, yet the insect remains alive. When warmth returns, water re-enters the tissues, metabolism resumes, and life continues as if months of severe cold were nothing more than a temporary pause. This remarkable adaptation demonstrates how far evolution can push the limits of biological survival. Snow cover also changes the paths of storms thousands of miles away. When a landscape becomes coated in bright, reflective snow, it sends incoming sunlight back into space instead of absorbing it. This rapid surface cooling alters temperature and pressure patterns above the snow, creating pockets of cold, dense air that behave differently from surrounding warmer regions. Storm systems respond to these differences, traveling along corridors shaped by pressure contrasts. As snow-covered regions expand or contract, these corridors shift, nudging storms onto new routes. A broad snow-covered area can act like a massive mirror, cooling the atmosphere over an entire region and reinforcing pressure systems that persist for days. This can redirect storms across continents, influencing where moisture falls, how strong weather fronts become, and which areas experience unusual patterns. Meteorologists track snow cover closely because it creates ripple effects that travel through the atmosphere far beyond the snowy region itself. Winter landscapes thus become active players in shaping weather, guiding storms that may originate thousands of miles away. Winter nights can also carry sound much farther than summer nights because cold air alters the way sound waves travel, especially when temperatures differ sharply between the surface and higher layers of the atmosphere. On winter nights, the ground cools rapidly, while the air just above it can remain relatively warmer. This temperature arrangement bends sound waves downward instead of allowing them to disperse upward. As a result, Noises from far away travel more efficiently and reach listeners clearly, sometimes covering distances multiple times greater than they would in warm seasons. The profound quietness of winter nights enhances this effect. Far-off trains, flowing water, barking dogs, crunching footsteps, and even human voices can seem strangely amplified. In this season of stillness, the landscape becomes a vast chamber where sound carries effortlessly across frozen fields and sleeping forests, creating a sense of expanded space. Thus, winter, through its cold, snow, soil, hidden life, and atmospheric clarity, reveals an entire world of subtle changes and quiet processes that remain unnoticed in warmer months, offering a reminder that stillness is never truly still, and silence is never truly silent. Winter transforms the world in ways that reach far beyond the chill felt on the skin, reshaping landscapes, ecosystems, and even the atmosphere itself through a complex interplay of temperature, moisture, physics, and biology. Snow-covered ground both absorbs and muffles certain sounds while simultaneously reducing wind and surface activity, leaving a quieter background in which distant noises, such as trains, vehicles, cracking ice, or the calls of far-off animals, travel with unusual clarity, demonstrating how temperature gradients reshape the invisible structure of the air and turn winter into a natural amplifier of acoustic effects. Ice crystals suspended in cold air create halos, arcs, pillars, and other geometric spectacles rarely seen in warmer months, as sunlight or moonlight refracts and reflects off millions of tiny hexagonal plates or columns that drift and orient themselves in alignment with gravity, forming glowing circles, shimmering arcs, and vertical beams that rise like illuminated towers above city lights. Frozen oceans behave like vast resonating bodies capable of producing deep booms, sharp pops, groans, and long rumbling tones as sheets of sea ice expand, contract, and fracture under the stresses of tides, currents, and shifting temperatures, with vibrations traveling great distances through the dense mediums of ice and water to reveal the thickness, structure, and tension of the frozen seascape in ways that explorers and scientists alike describe as eerie, melodic, or otherworldly. Winter temperatures reshape the boundary between land and atmosphere, causing very cold and dense air to settle against the ground in a stable layer that resists mixing with warmer air above, altering the flow of wind, the movement of humidity, and the circulation of gases. This can trap pollution and moisture into fog or haze, or in other regions create extremely clear skies and long-distance visibility. While frozen soil ceases releasing heat and moisture, forcing the atmosphere to adjust its energy balance and forming a new equilibrium that affects storm development, climate patterns, and regional weather. Snow acts as an incredibly effective insulator, trapping warmth beneath its thick white blanket and keeping soil temperatures relatively stable even when the air plunges into extreme cold, allowing roots, seeds, microbes, and dormant plant tissues to survive conditions that would otherwise destroy them. This insulating effect creates a subnivean zone, an entire hidden world between soil and snow, where temperature remains stable and small creatures like rodents can tunnel safely, sustaining entire ecosystems that depend on snow's protective properties for survival throughout winter's harshest months. Frozen rivers and lakes crack into patterns that resemble miniature tectonic plates as sheets of ice push, pull, collide, and separate under changing temperatures and the movement of water beneath them, producing ridges where they compress and channels where they stretch apart, forming webs of fractures and straight, branching, or intersecting lines that scientists study to understand stress distribution in solid materials, while casual observers marvel at the living, shifting geometry etched across the icy surface. Fresh snow, with its high albedo and multitude of reflective facets, scatters sunlight so intensely that winter landscapes often glow with brightness comparable to desert sands, affecting regional energy balance by reflecting heat back into space and creating feedback loops that preserve the snowpack. This brilliant reflectivity can cause visual discomfort or snow blindness in unprotected human eyes but is managed naturally by animals through anatomical and behavioral adaptations, while also enhancing distant visibility by increasing contrast across mountains, forests, and plains. Cold winter air holds far less moisture than warm air, reducing haze and scattering and producing conditions of remarkable clarity under calm skies, allowing distant features, mountains, cliffs, or far-off settlements, to appear crisp and sharply defined. The still, layered atmosphere acts like a natural telescope, and snow-covered terrain reflects light into shadowed areas to reveal contours and distant landmarks often hidden or obscured in summer's humid and turbulent air. Life across ecosystems slows dramatically as winter's cold sets in, reducing biological processes to near suspension as plants stop growing, animals hibernate or seek shelter, and insects either freeze solid or find specialized ways to avoid freezing. Yet beneath the snow, soil remains surprisingly active as microorganisms continue breaking down organic matter and recycling nutrients that plants will rely on when spring arrives. Some insects survive winter through extraordinary freeze avoidance strategies in which they remove water from their cells and convert internal substances to compounds that lower their freezing point, preventing ice crystal formation that would otherwise destroy tissues. Their metabolism slows to near zero, heart rate drops, and they enter a state of suspended life that reverses when warmth returns. As water re-enters tissues and biological activity resumes seamlessly after months of stillness. Snow-covered landscapes also influence weather patterns on continental scales by reflecting sunlight back into space, cooling vast regions of the atmosphere, and creating high-pressure pockets of cold, dense air that alter the pathways of storm systems. Expanding or shrinking zones of snow can nudge storms along new routes, change where and how moisture falls, and trigger ripple effects across thousands of miles as meteorologists track these variations to understand and predict atmospheric behavior. Winter is a season defined by contrast between movement and stillness, silence and resonance, clarity and opacity, deep cold and the warmth tucked safely beneath snow, and each of these contrasts reveals a deeper structure to the natural world. Ice crystals drifting in the air create visual geometry in the sky. Frozen seas communicate their stresses through booming vibrations. Cracks on frozen rivers mirror continental tectonics. And vast blankets of reflective snow transform both the brightness of local landscapes and the behavior of distant storms. Beneath the surface, hidden ecosystems persist under snow's insulation. Underground networks of microbes and roots stay active, and animals carve secret paths through subnivean corridors, proving that winter is far from a season of death or silence. Rather, it is a season of slowed rhythm, structural revelation, and quiet resilience. The atmosphere itself becomes a medium through which sound travels farther, light refracts into rare optical wonders, and distant landscapes appear with newfound sharpness, while the frozen ground reshapes thermal exchanges, alters wind patterns, and redraws the interface between earth and air. Every crack in the ice, every halo around the sun, every long-distance echo and amplified whisper in the night air tells the story of a world temporarily transformed by cold into a realm where physics, biology, and atmosphere interact in ways that remain hidden during warmer seasons. Winter, with all its challenges and stark beauty, becomes not just a pause in the year's cycle but a period of extraordinary transformation, an expansive laboratory in which light, sound, energy, and life itself behave differently, quietly revealing the deep connections that tie together the land, sky, water, and living creatures that endure the coldest months of the year. As temperatures drop, chemical reactions inside living organisms proceed more slowly, reducing energy demands and altering the way cells function, and many species rely on this slowdown to survive harsh conditions, with some reptiles and amphibians entering states in which movement stops almost entirely and heartbeats become faint. While microorganisms reduce their activity to minimal levels to conserve resources until warmth returns, even plants participate in this shift as their cellular machinery changes, water content decreases, and growth halts, creating a suspended state that protects tissues from freezing damage and prevents metabolic stress. And this slowing of biological processes influences entire ecosystems, as predators hunt less, prey move less, and the flow of energy through food webs becomes subdued, only to surge again when spring arrives and temperatures climb, resetting life across large regions and demonstrating the profound control temperature has over the rhythm of living systems. While snow itself can grow layers that store precise records of weather over time, with each storm leaving behind a distinct layer shaped by temperature, humidity, wind, and crystal type, and as these accumulate they compress but remain separated by differences in texture, density, grain size, or trapped air, forming a seasonal archive readable through snow pits where a fluffy layer reveals calm snowfall and dense rounded snow points to winds that packed it tightly, while thin crusts show brief sunlight warming before temperatures plunged again, and dust or pollen create thin lines signaling the timing of particular weather events, and deeper layers undergo slow transformation under pressure but still retain recognizable patterns, each winter leaving a fingerprint of storms, warm spells, cold snaps, and atmospheric behavior that in long-term snow regions forms the foundation of glaciers. Turning delicate snowfall into a frozen environmental record, ice in lakes, rivers, and seas can form floating sheets that collide and grind like miniature tectonic plates, behaving not as a uniform slab but as shifting sections responding to currents, wind, and temperature, drifting and colliding to form ridges or buckling zones, sometimes sliding over each other like miniature subduction zones, and where they pull apart, long cracks called leads reveal the dark water beneath, creating a constantly changing mosaic that scientists study to understand stress in solid materials, while experienced winter travelers read these patterns to determine safe or dangerous routes, reminding anyone watching that frozen water is anything but static and instead acts like a living, responsive surface. Winter clouds also differ from summer clouds as they often contain more ice than water because droplets freeze into tiny crystals in the cold, with even liquid droplets becoming supercooled and ready to freeze with the slightest disturbance. And once ice forms, water vapor clings more easily to solid surfaces, creating crystals, plates, needles, columns, or branching forms that fill the cloud, reflect sunlight in unique ways, and create halos and arcs impossible in liquid-based clouds, influencing how precipitation forms as crystals grow and fall as snow or sleet, even when ground temperatures remain above freezing, giving winter clouds their own chemistry and optical signature. Cold weather also dramatically amplifies certain smells because dense, still air slows the dispersal of odor molecules, allowing scents to linger and concentrate near ground level, and the human sense of smell becomes slightly sharper in cold because molecules remain more stable and break down more slowly, so forests, industrial zones, and neighborhoods often smell different in winter, with wood smoke, soil, or vegetation becoming more distinct, while frost and smoke can trap odors that release once sunlight warms the surfaces, creating winter scent patterns that differ entirely from warmer seasons, showing that winter does not mute the world but instead selectively enhances sensory signals. Frozen lakes can produce mysterious rings and circles, sharp-edged patterns that form without warning and vary in size and shape, caused by warm underwater springs that thin ice in circular zones, rotating eddies carving spirals beneath the surface, or methane rising from sediments to melt circular patches, features that researchers study with drones and satellite imagery. And to observers these circles seem almost intentional, like art drawn by unseen forces beneath the ice. Winter storms themselves can move heat between continents by tapping into warm ocean currents, pulling that energy into cold air masses, and releasing it through condensation as clouds form, altering the storm's structure and downstream temperatures, shifting jet stream pathways, influencing regional warmth, or cold, and participating in global heat balance by transporting warmth from some areas and delivering cold to others, affecting ocean temperatures, atmospheric moisture, and even long-term climate trends, making winter part of a planetary energy transfer system rather than just a local seasonal event. Snow that falls on the ocean behaves differently from snow on land because ocean water absorbs heat and moves constantly, often melting falling snow into a thin freshwater layer that sits atop denser salt water and alters salinity, temperature, wave behavior, and heat loss. And when sea ice forms, snow on top can push the thin ice downward enough for seawater to flood it, freezing into a unique type of sea ice unlike ice formed directly from ocean water, while snow also insulates sea ice, slowing its growth yet protecting it from melting during sunny winter days, all of which affects thickness, strength, and drift in polar regions, shaping weather, climate, and ecology. Winter can even create natural lenses made of ice when water freezes into clear, bubble-free structures capable of bending sunlight, casting bright focused spots on the snow below or projecting distorted images. And when these naturally formed ice lenses melt and refreeze, They generate evolving optical effects across the winter landscape, adding another layer of subtle visual phenomena to the season. Droplets that freeze into spheres on branches or rocks become tiny natural lenses that magnify the patterns beneath them, bending incoming light in subtle ways that reveal textures and details invisible during warmer seasons. And larger curved surfaces on frozen lakes can focus sunlight into bright patches that drift slowly across the ice as the sun moves overhead, creating shimmering, fluid patterns that seem to glide with time itself. Even small variations in the thickness of clear lake ice can create optical distortions that stretch, warp, or compress objects seen through the frozen layer, turning stones, plants, or submerged debris into ghost-like shapes that shift as the viewer walks. Under certain conditions, cycles of melting followed by rapid refreezing can produce smooth domes of ice that act like magnifying glasses, offering glimpses of the world below with surprising clarity. People walking across transparent ice may see pebbles, bubbles, plants, or fish distorted into unexpected forms as the frozen surface bends and refracts light. Winter thus becomes a season filled with unintentional optical experiments created by the quiet interaction of sunlight, temperature, and frozen water, turning ordinary landscapes into galleries of ephemeral optical effects. Meanwhile, frozen ground can trap gases that reactivate when thawed, as soil freezes from the surface downward, locking moisture and gases in place and sharply slowing microbial activity so that organic material sits largely undisturbed beneath the cold crust. As the freeze deepens, carbon dioxide, methane, and other gases that normally escape into the air become sealed within tiny ice pores. When spring warmth returns and thawing begins, these gases are released in rapid pulses that signal the awakening of soil life. In wetlands and tundra regions, the effect is especially strong because large amounts of organic matter accumulate throughout the year, and once thawed, microbes resume breaking down this material, accelerating gas release and reshaping soil chemistry, moisture, and biological rhythms. This freeze and thaw cycle influences ecosystems, seasonal growth patterns, and atmospheric composition, demonstrating how deeply winter controls the movement of energy and matter through the ground. Snow grains, too, evolve into new shapes long after they fall, because a snowpack is not a static blanket but a dynamic system driven by temperature gradients between the warmer ground and the colder upper layers. Water vapor migrates upward through the pack, transforming individual grains through metamorphism in which rounded grains grow into angular forms, facet into sharper shapes, or fuse into stronger clusters depending on the thermal structure of the snowpack. In some cases, grains bond together to create firm, supportive layers. In others, the structure weakens, becoming prone to collapse or avalanche. These transformations depend on depth, sunlight, humidity, and the amount of trapped air between grains, and over time the snowpack becomes a layered, evolving archive with distinct mechanical properties, demonstrating that even a simple mound of snow is a living material shaped by subtle exchanges of energy and moisture. Ice can also build delicate structures on plants that mimic the growth of minerals, as super cold droplets floating in winter air freeze instantly when they touch surfaces slightly colder than themselves, coating branches, stems, grasses, and seed heads with crystalline formations that resemble feathers, blades, or mineral fans. Instead of hanging downward with gravity, these ice projections grow outward in the direction of the wind, shaped by humidity, airflow, temperature, and the micro-textures of the plant itself. Even a gentle shift in the breeze can redirect their growth, creating layers that twist or curve, forming temporary sculptures that glow softly when touched by early morning light. Though fragile and short-lived, these formations demonstrate how the simplest interactions between moving air and freezing moisture can produce patterns that appear deliberate and artistic. At much larger scales, winter pressure patterns shape entire regional climates, as cold season atmospheric pressure systems guide the movement of air masses across continents and influence temperature, rainfall, snowfall, and storm tracks for months at a time. Winter cooling increases the contrast between warm and cold regions, creating zones where air becomes dense enough to sink and spread outward, forming persistent high-pressure systems that can lock cold air in place or block incoming warm currents. Meanwhile, low-pressure centers steer storms along predictable paths, bringing heavy snowfall to some areas while leaving others cold and dry. Even slight shifts in the strength or position of these pressure systems can change the character of an entire season, determining whether a region receives frequent storms, unusual warmth, extreme dryness, or long stretches of frigid calm. Scientists study these patterns because their influence extends from atmospheric circulation to ocean behavior, agricultural productivity, and long-term climate. Inside homes, frost can form patterns that map air flow across a window. As moist indoor air meets a cold pane and tiny droplets condense and freeze, creating intricate branching shapes that follow humidity gradients, temperature differences, and air currents within the room. Warmer areas on the glass remain clear while colder spots attract more frost, and airflow from heaters, vents, open doors, or even a person walking by can redirect the growth. Microscopic imperfections on the glass act as anchor points where crystals begin to spread, making each window a unique landscape of frost that responds to the changing conditions of the room. Viewed closely, these patterns become maps of heat transfer and air movement frozen into delicate crystalline architecture. Outdoors, cold air can create mirages usually associated with deserts, because extremely cold, dense air bends light along curved paths when temperature differs between layers near the ground. This bending allows distant objects to appear lifted upward above the horizon, forming looming mirages that make trees, buildings, mountains, or entire coastlines appear taller, sharper, floating, or distorted. Snow-covered plains and frozen lakes are especially prone to these optical illusions because their smooth surfaces cool the air evenly, creating strong refractive layers that warp the appearance of distant landscapes. In rare conditions where warm and cold air stack in alternating layers, highly complex distortions can occur, causing objects to flicker, stretch, or replicate into multiple images. These winter mirages reveal how sensitive human vision is to the structure of the atmosphere and how temperature alone can restructure the world we see. Deep within ice sheets, ancient bacteria become trapped and preserved for centuries or even millennia as layers of snow build up year after year. Dust, pollen, organic particles, and microorganisms become sealed within the growing ice, protected by cold, darkness, and extremely slow chemical activity. Some bacteria enter dormant states that allow them to survive without sunlight or nutrients for astonishingly long periods, and when scientists drill into glaciers or polar ice and bring these organisms into the laboratory, some revived microbes show signs of life when exposed to warmth and moisture again. Their survival reveals the extraordinary resilience of life and offers insight into how organisms might persist on other frozen worlds where conditions resemble Earth's ancient ice. Even winter storms contribute to the planet's dynamic system by lifting tiny particles into the stratosphere, as powerful updrafts inside large storm systems carry fine dust, ash, sea salt, and organic matter far above typical cloud layers, injecting materials into high altitudes where they influence cloud formation, atmospheric chemistry, and the scattering of sunlight. These processes demonstrate that winter is not a dormant season but a period of intense, varied, and subtle physical activity, transforming landscapes from microscopic frost patterns to continental weather systems, and revealing the hidden complexity of the coldest months of the year. Hello there, and welcome to Science for Sleep. Ice reveals an entire hidden world where the familiar rules of nature bend, distort, and magnify themselves into phenomena that seem almost unreal, creating a display in which reality becomes subtly rearranged and light behaves differently as temperature shifts, showing just how sensitive illumination is to even the smallest variations in heat and cold. Across frozen landscapes, massive sheets of ice trap ancient bacteria that may reawaken when warmth returns, offering glimpses into biological endurance that stretches across millennia. Layers of snow accumulate year after year, compressing older deposits beneath them and forming stratified records of dust, volcanic ash, microorganisms, and organic particles, all sealed in cold darkness where decay slows to almost nothing. Some bacteria enter dormancy, surviving without sunlight or nutrients for extraordinary periods, their genetic structures preserved by adaptations designed to protect them from freezing, radiation, and chemical assault. When scientists drill deep into glacial ice or polar sheets, they sometimes retrieve these minute survivors, and when brought into a laboratory and gently warmed with moisture, many revive and begin to function again, showing that life is far more persistent than we imagined and raising the possibility that similar organisms could withstand the extreme cold of distant planets and moons. Ice is not merely frozen water, it is a vault of past environments, storing the fingerprints of ancient climates and, in rare cases, living material that quietly describes the resilience of Earth's smallest inhabitants. Winter storms also possess an overlooked power. During periods of intense cold, strong updrafts can rise inside massive storm systems, lifting tiny particles of dust, salt, ash, and organic matter high above the clouds. Under the right conditions, these particles cross the boundary into the stratosphere, a region typically unreachable by ordinary weather patterns. Once there, they can linger for months or years because the stratosphere is calm compared to the turbulent lower atmosphere. Scientists track these lofted particles to understand how storms transport material across continents and oceans, influencing chemical reactions in the upper atmosphere, filtering sunlight, and even shifting climate behavior on broad scales. Every powerful winter storm becomes a participant in a global cycle, moving matter far beyond its origin and depositing it in places where it may remain suspended for extraordinary stretches of time. Cold also turns soil into an unexpected archive. When the ground freezes, moisture within it solidifies and strengthens the surface, allowing it to capture impressions from animals with incredible clarity. Tracks pressed into frozen soil remain intact far longer than those in soft snow or thin ice, retaining the fine details of claws, pads, and stride patterns. Wildlife trackers rely on these prints to understand the movement, health, and behavior of species, particularly in regions where animals are elusive. A brief thaw may soften the ground just long enough to create a perfect impression, and the following freeze locks it into place like a natural cast. Such tracks represent a precise moment in time, a leap, a pause, a sprint, or a slow wandering preserved until warmer weather arrives to erase it. Frozen landscapes hold these secret stories, and the imprints reveal population movements, feeding habits, territorial boundaries, and other subtle clues that vanish once the soil thaws in spring. Materials themselves behave strangely in winter. Paints that remain flexible during warm months stiffen in the cold, their pigments and binders separating slightly and forming cracks as the surfaces beneath them contract. Plastics become brittle as molecular motion slows, making them vulnerable to snapping, deforming, or shrinking in uneven patterns that weaken joints and stress points. These changes remind designers that all materials have limits, and objects intended for winter must account for forces far more complex than simple temperature drop. Cold conditions expose the hidden weaknesses in everyday materials, revealing the invisible molecular choreography that underpins their structure and function. As wind sweeps across open fields of snow, it shapes the surface into dunes that resemble those found in deserts. Unlike heavier sand, snow moves easily, and even gentle breezes push dry crystals into rippling ridges that stretch across the ground. These snow dunes evolve constantly, migrating across landscapes as shifting winds sculpt their peaks and troughs. Some dunes rise only a few centimeters, while others appear like miniature mountain ranges extending across large plains. Their patterns reveal information about wind direction, turbulence, snow grain structure, and the stability of the underlying snowpack. Snow, though soft and delicate, responds to the same physical forces that shape deserts, and during the winter months it forms a dynamic terrain that changes daily. Along coastlines and polar seas, winter water behaves even more strangely. When seawater begins to freeze, the forming ice pushes out most of its salt, trapping the concentrated brine in narrow, branching channels that weave through the ice like hidden rivers. These brine channels remain liquid even in extreme cold because their salinity lowers the freezing point significantly. As temperatures rise or fall, the channels expand or contract, changing how water, salt, and heat move through the ice. Inside these narrow pathways, microorganisms flourish, forming small ecosystems that thrive in chemical compositions and pressures that would be lethal elsewhere. These channels also influence how sea ice thickens, fractures, melts, and interacts with the ocean below. The brine sinks through openings into the seawater, altering its density and affecting the circulation of entire regions, which in turn shapes weather patterns and marine habitats. Beneath the apparent stillness, winter sea ice teems with activity, revealing a complex structure far more dynamic than a simple frozen sheet. On lakes, rivers, and coastlines, ice often fractures with the force of miniature earthquakes. As temperatures rise and fall, large sheets of ice expand and contract, storing tension until it releases suddenly in sharp cracks that send vibrations racing across the frozen surface. Sensitive seismographs sometimes record these fractures as tiny quakes because the energy travels similarly through solid material. People standing nearby may hear loud booms, deep rumbles, or high-pitched whips echoing across the ice. The cracks can travel for astonishing distances, carving long, branching lines across miles of frozen surface, sometimes visible from shore to shore. These ice quakes highlight how even frozen environments are constantly shifting, bending, and readjusting, mirroring the geological processes that move continents and mountains on a much slower scale. Rare winter storms can also create unusual spherical ice pellets, small, dense balls of layered ice that form when supercooled droplets freeze around a tiny central nucleus. Unlike hail, which requires powerful updrafts in warm-season storms, these pellets form at lower altitudes in cold conditions where the temperature layers are very specific. As they tumble through turbulent air, layers build smoothly around them, creating icy beads that bounce when they strike the ground. Their appearance requires a perfect arrangement of humidity, temperature layering, and air motion, making them an infrequent but fascinating form of precipitation. Within storm clouds, countless micro-interactions between water droplets, ice crystals, and temperature gradients produce these shapes, revealing the extraordinary complexity hidden inside winter weather systems. And beneath all of this, the snowpack builds quietly throughout the season, storing vast amounts of frozen water that may lie still for months until spring sunlight triggers rapid melting. Snow accumulates in layers, each with its own density, structure, and temperature. Some layers are loose and airy, while others compress into dense slabs capable of holding tremendous weight. As winter progresses, these layers interact, strengthen, weaken, and shift internally, making the snowpack a dynamic system that hides an enormous reservoir of moisture. When spring arrives and temperatures rise, meltwater flows downward through the layers, sometimes pooling until it suddenly releases, causing floods or rapid runoff events that reshape rivers and landscapes. The snowpack becomes a slow-moving, temporary water storage system that influences groundwater, agriculture, ecosystems, and regional climate patterns. Throughout winter, it acts as both a record of storms and a reservoir waiting to awaken. In all these ways, winter transforms landscapes into living laboratories where the interactions of cold, light, moisture, wind, and time reveal surprising behaviors in materials, ecosystems, and the planet itself, forming a world in which ice records the past, storms rearrange the present, and frozen water continues to remind us how profoundly temperature shapes the natural world. The density of snow changes over time as individual grains gradually fuse, settle, and rearrange themselves under their own weight, hiding significant amounts of water beneath what often appears to be a soft, powdery, lightweight surface, and in regions where deep winter snowfall is common, this hidden reservoir becomes one of the most important contributors to rivers, lakes, wetlands, and groundwater once spring returns with warmer temperatures that trigger widespread melting. This melting process is not uniform across landscapes, because when spring temperatures rise quickly, meltwater can flow more rapidly across the surface than soil and vegetation are able to absorb, leading to sudden increases in stream flow, rapid rises in lake levels, and in extreme cases, flash flooding that reshapes riverbanks and washes away accumulated debris. Mountain regions are especially sensitive to these rapid changes because elevation influences temperature, creating a patchwork of slopes that warm at different times and speeds. South-facing slopes may warm early, releasing water quickly, while shaded slopes remain frozen longer, delaying meltwater release and creating staggered surges. As snow melts, it does not simply disappear from the surface but undergoes an internal transformation, carving new pathways that shift constantly as channels form, collapse, redirect, and merge deep within the snowpack. Scientists carefully monitor snow depth, density, temperature, and layering to predict how much meltwater will enter watersheds each season, because these predictions guide decisions about reservoir management, flood control, agricultural planning, energy generation, and even drought preparation. Snowpack is therefore far more than seasonal decoration sprinkled across winter landscapes. It acts as a temporary but massive natural reservoir, storing water that entire regions depend on for drinking supplies, irrigation, ecosystems, and hydroelectric power. On frozen lakes, winter creates another remarkable phenomenon: the trapping of methane beneath clear sheets of ice, forming transparent domes that rise like glass bubbles suspended in frozen surfaces. Methane is produced naturally at the lake bottom when organic materials such as dead plants, algae, and sediments decompose in oxygen-poor environments. During warm months, the gas escapes easily into the atmosphere, but during winter a thick layer of ice prevents its release, causing bubbles to accumulate beneath the frozen surface where pressure pushes upward, stretching the ice into curved, dome-like shapes. These domes come in a wide range of sizes depending on the strength of the ice, the rate of methane production, and how long the gas has been accumulating. In some lakes, dozens or even hundreds of these glass-like bubbles appear across the surface, creating surreal patterns of stacked white circles frozen at different depths, each representing a separate pulse of gas released from the lake bed at a different moment. When spring arrives and the ice finally fractures, the domes burst and the trapped methane escapes into the air in a rapid release. Researchers study these frozen formations to better understand methane emissions, lake ecosystem activity during winter, and the influence of seasonal freeze-thaw cycles on greenhouse gases. Each bubble acts as a miniature archive of underwater biological processes that continue throughout the winter, hidden beneath the silent, frozen surface. Winter also affects the sky above in ways that might go unnoticed, particularly in how birds adjust their flight patterns based on the changing density of cold air. As temperatures drop, air molecules move closer together, making the atmosphere denser. This increased density provides greater lift on bird wings and changes how air flows across their bodies during flight. Many bird species respond to this shift by subtly altering their wing beats, gliding intervals, and flight paths to take advantage of the seasonal changes in lift and drag. Some species are able to glide longer distances with less energy expenditure because the denser winter air provides stronger aerodynamic support, while others adjust their flying altitude to remain within atmospheric layers where efficiency is highest. Even slight variations in air density influence how flocks coordinate their movements, affecting spacing, formation stability, and how birds communicate subtle directional changes. Migratory birds flying long distances through cold regions must account for these seasonal aerodynamic differences, making winter flight mechanics distinct from those in warmer months. Observations of winter bird movement reveal a highly refined relationship between living creatures and the invisible physical properties of the atmosphere, showing that birds use winter air as a natural tool, adjusting their techniques to maintain speed, conserve energy, and avoid turbulence. Winter also transforms the behavior of radio waves, altering how signals travel across the atmosphere. Cold season atmospheric layers often become sharply stratified, with dramatic temperature contrasts between the ground and higher altitudes. This layering can cause radio waves to curve along the boundaries between layers, allowing signals to travel much farther than normal. Temperature inversions, situations where a layer of cold air becomes trapped beneath warmer air, create a reflective boundary that prevents radio waves from escaping upward and instead causes them to bounce horizontally across long distances. This phenomenon strengthens communication signals during winter nights, allowing broadcasts to reach locations hundreds of miles from their source. Reduced humidity and the clarity of cold winter air also allow certain frequencies to propagate with less interference, increasing the likelihood of receiving distant stations unexpectedly. Engineers study these effects to improve communication technologies and understand how atmospheric structure influences signal pathways. Winter, with its distinctive temperature gradients and stable layers, becomes a natural laboratory that reveals the hidden interactions between electromagnetic waves and the environment. Even snow itself interacts with light in surprising ways, capable of glowing under ultraviolet illumination. The surface of fresh snow is composed of countless ice grains that scatter light in all directions, and under ultraviolet radiation some of these grains reflect and refract wavelengths that create a faint, eerie glow visible under the right conditions. This glow is not typically noticeable in everyday daylight because bright visible wavelengths overwhelm the ultraviolet reflection, but in controlled environments, or in high-altitude regions where ultraviolet radiation is strong, the glow becomes much more pronounced. Its brightness depends on the purity of the snow, the shape of individual grains, and the quality of the light source shining upon it. Researchers study this ultraviolet response to better understand how snow interacts with incoming solar radiation and how the reflective properties of snow influence the planet's overall energy balance. What may appear to be a simple white blanket is actually a highly complex surface capable of scattering an enormous range of wavelengths in ways that reveal the intricate optical structure of frozen water. Even within clouds, ice crystals behave in ways that challenge our assumptions. Under specific winter conditions, tiny ice crystals form in remarkably stable layers of cloud where temperature, humidity, and subtle air motion remain balanced. These crystals are incredibly light and often grow into shapes, such as thin plates or feathery dendrites, that increase drag and slow their descent. Gentle upward air currents can counteract gravity just enough to keep the crystals suspended for long periods, during which they continue to grow by collecting water vapor from the surrounding air. Some crystals remain aloft for hours or even days until they merge with other crystals, encounter turbulence, or drift into regions where air motion changes. Their extended residence time influences cloud brightness, precipitation development, and the scattering of sunlight. Scientists study these suspended crystals to better understand cloud dynamics, atmospheric circulation, and the development of storms. Each crystal becomes a tiny tracer particle that reveals the hidden movements of air within storm systems and high-altitude cloud decks. Winter temperature swings also reshape the solid landscape by carving grooves into stone through repeated cycles of expansion and contraction. Rock surfaces warm slightly under sunlight, causing the outer layer to expand, and then contract again when exposed to freezing nighttime temperatures. Over countless cycles, microscopic cracks open and close, weakening the rock's surface. When water enters these cracks and freezes, it expands, widening the gaps and lifting small flakes or fragments from the rock face. Over time, this process, known as freeze-thaw weathering, produces grooves, pits, and channels that subtly alter the shape of stones. These features develop more rapidly in regions where winter brings dramatic daily temperature shifts between warm afternoons and freezing nights. Different rock types respond differently depending on their mineral composition, internal structure, and existing weaknesses. Though the changes occur slowly, they accumulate into permanent modifications that record the environmental conditions responsible for shaping them. Snow cover also plays a powerful role in regulating Earth's reflectivity, or albedo. Large areas covered with bright, fresh snow reflect a significant portion of incoming sunlight back into space, cooling the surface and lowering air temperatures. When snow persists across continents or high latitudes, it becomes a major factor in the planet's energy balance, influencing how much solar energy the Earth absorbs and how much it sheds. Even modest changes in snow extent can alter regional climates by shifting the amount of heat transferred between land and atmosphere. For this reason, scientists closely monitor snow cover using satellite imagery and ground measurements, tracking how it interacts with cloud formation, storm tracks, and long-term climate trends. Snow acts simultaneously as a shield that deflects sunlight and as a regulator that controls how quickly the surface warms or cools. Whether cold conditions intensify or weaken across a region often depends largely on the presence or absence of snow cover. Frozen water also stores atmospheric history in layered ice formations that can preserve decades or even centuries of environmental data. When snow accumulates year after year on glaciers or ice sheets, it compresses into distinct layers of ice, each one trapping tiny samples of the atmosphere from the moment it formed. These layers contain traces of gases, dust, volcanic ash, pollen, ocean salt, wildfire smoke, and even microorganisms that drifted through the air at the time. As new layers form above, the deeper ice becomes a chronological archive sealed beneath stable cold conditions. Scientists drill deep cores into this layered ice to study the chemical signatures locked inside. Each layer provides clues about past temperatures, atmospheric composition, solar intensity, ocean circulation, and even ancient weather patterns. Aromas rely on delicate volatile compounds that evaporate easily in warm conditions, carrying scents upward where they can reach the nose and shape what we interpret as flavor. But when winter arrives and the air becomes cold, dense, and unmoving, far fewer of these molecules lift away from the food, causing aromas to weaken noticeably and making dishes seem unexpectedly muted even when the ingredients remain the same, demonstrating how profoundly temperature shapes our sensory experience. Because more than half of what humans call taste is actually the result of smell, this reduction in fragrance directly alters our perception of richness, sweetness, bitterness, and even texture, creating the illusion that the food itself has changed when in reality the environment is reshaping the chemistry between our senses and the particles rising from the plate. At the same time, winter air can heighten awareness of sharper or salter flavors because the coolness inside the mouth and nasal passages reduces interference from humidity and prevents overwhelming scents from dominating the palate. This shift becomes especially obvious during outdoor winter activities or in homes where drafts lower indoor temperatures. A warm drink suddenly feels more intense and comforting because the steam rising from it carries a concentrated plume of aroma directly into the cool air, while a chilled dessert or refrigerated dish may seem flat and bland because its scent remains trapped close to its surface, unable to diffuse freely. Thus, winter influences flavor not simply through temperature but by altering the physics of odor molecules, the density of the air, and the way the senses interpret chemical signals, turning every bite into a subtle interaction among heat, moisture, and movement. In equally surprising ways, frost can grow outward from warm objects, forming delicate crystalline structures that seem to defy the intuitive direction of freezing. When a warm or slightly heated object sits in very cold air, moisture from the surrounding environment condenses on its surface and freezes immediately, forming the first thin layer of frost. As the object continues to lose heat slowly, the frozen coating thickens, while new moisture lands on the diminishing warm boundary around the object and freezes just beyond the previous layer. Over time, this process repeats in a pattern of outward growth, producing feathery fingers of ice that extend into the air like miniature sculptures shaped by invisible hands. The shape of these structures reflects the movement of air and the gradients of temperature surrounding the object. Steady airflow causes frost to grow like a leaning forest pointing downstream, while still air creates nearly symmetrical, lacy expansions that radiate evenly in all directions. Pipes, wires, vents, and even branches often display this behavior because they remain warm enough to draw moisture toward them while still cold enough for immediate freezing, producing exquisite frost arrangements that act as visible reminders that freezing is not a static event but a dynamic, energy-driven process shaped by the interplay of heat loss, humidity, and surface temperature. Winter ice also demonstrates astonishing complexity beneath our feet, sometimes freezing into vertical column structures that appear almost man-made in their precision. Under specific conditions, water within soil freezes not as a solid sheet but as upright pillars when intense cold penetrates the ground more quickly from above than moisture can escape from below. As the surface freezes, ice crystals grow downward and pull liquid water upward through tiny pathways in the soil, continuing to lengthen until they form parallel columns of translucent ice that can rise several centimeters above the ground. These columns, often called needle ice, can lift stones, soil, and bits of organic matter as they grow, creating uneven surfaces that crunch loudly when stepped on. Their formation depends on a combination of soil moisture, the rate of heat loss, and fluctuations in temperature that determine whether the columns continue growing or collapse into glittering fragments. When cold persists consistently, the columns become taller and more pronounced, but when temperatures rise and fall, they weaken and topple, leaving behind scattered, sparkling debris on the ground. These formations demonstrate how freezing can reorganize the structure of the Earth in ways that seem like deliberate engineering, reshaping the landscape through a process that is invisible until the final result appears. Far from being lifeless, winter ice also hosts complex microbial ecosystems that survive, grow, and transform beneath frozen surfaces. In polar regions, the surface of the ocean freezes into large sheets that gradually develop intricate networks of brine-filled channels within them. The salt within seawater is pushed out as ice forms, creating pockets of dense, salty liquid that remain unfrozen even in extreme cold, and these brine channels become winding habitats home to a surprising variety of microorganisms adapted to limited nutrients, low light, and freezing temperatures. These microbes feed on dissolved organic matter, form layered communities on the interior walls of the ice, and support tiny grazers that feed on them, creating an entire food web hidden within the seemingly solid surface. As sunlight begins to filter through the ice during late winter and early spring, photosynthetic organisms awaken and begin producing energy, fueling bursts of biological activity that affect nutrient cycling in the surrounding water. When the ice melts each season, millions of organisms flow into the ocean below, triggering pulses of productivity that ripple through polar food webs and influence the behavior of fish, plankton, and larger animals. This hidden world reveals that ice is far more than frozen water. It is a structured environment capable of supporting life with remarkable resilience. Frozen waterfalls exhibit their own mysterious behaviors, trapping the sounds of flowing water beneath their crystalline surfaces. When temperatures drop rapidly, the outer layer of a waterfall can freeze even as water continues rushing beneath it, carving tunnels, pockets, and hollow chambers inside the ice. These cavities act as natural resonating chambers that distort and amplify sound, transforming the familiar roar of unfrozen water into deep hums, echoing vibrations, and delicate tapping noises where thinner layers of ice respond to movement. As temperatures fluctuate, cracks open and close, altering the acoustic landscape and creating shifting soundscapes that change from day to day. People standing near these frozen waterfalls may hear muffled thunder beneath their feet or soft chimes that seem to emerge from within the ice itself, experiencing a natural instrument whose tone evolves with the weather. This phenomenon shows how freezing separates the motion of water from the environment around it while still allowing its energy to resonate through the frozen structures, linking the visible stillness of winter with the hidden dynamism beneath the surface. Snow also participates actively in the exchange of sunlight and heat, converting light into warmth through subtle chemical reactions. Although snow reflects a large portion of the sunlight that strikes it, certain wavelengths penetrate the upper layers and interact with impurities such as dust, soot, or organic molecules embedded in the snowpack. These impurities absorb energy and trigger tiny chemical reactions that release small amounts of heat. Winter's influence on the natural world extends far beyond the obvious chill, shaping landscapes, altering energy flow, and revealing hidden structures as cold air, frozen ground, shifting winds, and crystallizing water interact in ways that are often subtle but immensely powerful. In coastal regions, winter storms can strip away the uppermost layers of sand and sediment, exposing long-buried geological structures that have remained hidden for seasons or even years, as the relentless wind scours away loose particles and reveals the hardened surfaces beneath. Meanwhile, in deserts, where cold air settles heavily over the ground at night and reduces the movement of individual grains, sand becomes temporarily stabilized, allowing fine particles to accumulate into delicate ridges and contours that mimic the shapes of dunes yet vanish almost instantly as soon as warmer daytime winds dissolve the cohesion. During these colder months, the landscape transforms into a canvas upon which winter forces paint intricate patterns shaped by frozen surfaces, persistent winds, and the dynamic exchange between temperature and terrain. Cold air also has the remarkable ability to reveal heat signatures that would otherwise remain invisible during the warmer parts of the year. When temperatures drop far below the warmth radiating from objects on the ground, even small sources of heat, like buried pipes, the trunks of trees, or the exhaust of recently parked vehicles, become sharply defined against the frigid environment. Viewed through thermal imaging, the contrast becomes striking. Buildings glow with uneven heat loss, wildlife trails stand out like glowing threads across snowy fields, and footprints linger long after they've been made, each print briefly preserving the warmth of the body that created it. Researchers often take advantage of these conditions to analyze energy efficiency in structures, track animal behavior, and study how heat transfers through soil, vegetation, and infrastructure. Winter, in this sense, acts like a magnifying lens that exaggerates thermal contrasts and provides a unique perspective on the hidden patterns of energy moving through the environment. Frost's remarkable ability to split rock emerges during the relentless cycles of freezing and thawing that accompany winter. When water seeps into tiny cracks during the day and freezes at night, it expands with enough force to widen the fissure. Although each cycle produces only a minuscule change, the cumulative effect can be dramatic, gradually prying apart rock surfaces, generating loose debris, and reshaping cliffs or boulder fields over many years. In areas where freeze-thaw cycles occur frequently, this process becomes one of the primary mechanisms through which mountains slowly break down, sediment accumulates at the base of slopes, and landscapes evolve in response to seasonal variations. Winter also transforms the acoustic behavior of natural environments, turning valleys, forests, and frozen lakes into enormous resonating chambers that amplify some sounds while muting others. Fresh, dry snow behaves like an acoustic sponge, absorbing higher frequencies and creating quiet, softened surroundings, whereas smooth ice on lakes reflects sound with exceptional clarity, enabling even distant noises to travel across the surface with surprising sharpness. Temperature inversions, when a layer of warm air sits above cold air trapped at the ground, can bend sound waves downward rather than allowing them to dissipate upward, making distant cracks, calls, or footsteps seem unusually close and astonishingly loud. Frozen forests, stripped of their flexible summer leaves, transmit vibrations differently, giving winter its own unique acoustic profile shaped by temperature, density, and texture. Far beneath the frozen surfaces of northern landscapes, ancient ecosystems lie locked in permafrost, preserved for thousands of years by the continual cold. Long ago, immense forests of birch, spruce, and other species thrived in regions that are now barren tundra. When global climates shifted, these forests died back and became buried under layers of sediment, peat, and eventually permafrost. The cold arrested microbial decay and sealed out oxygen, preserving roots, leaves, seeds, and even entire tree trunks in astonishing detail. Today, researchers excavate these frozen remains to reconstruct ancient ecosystems, study the climate cycles that shape them, and understand how rapidly environmental conditions can change. Some of these preserved forests contain evidence of ancient fires, insect infestations, and weather patterns that unfolded long before humans kept records. The tundra thus functions as a time capsule, holding the remains of long-lost worlds and quietly documenting Earth's climatic past. Winter can also turn lakes into transparent sheets of ice so clear that the bottom becomes visible, creating the illusion of walking on air. This phenomenon occurs when dry, extremely cold air draws heat from the surface quickly, causing ice to freeze with minimal imperfections, few trapped bubbles, and virtually no suspended particles. If the water beneath is calm and clear, the resulting ice forms a window into the depths below, revealing stones, aquatic plants, and even moving fish, all sharply visible beneath the thick frozen layer. As the ice grows thicker, internal stresses form long dark fractures that create elegant patterns without compromising the surface's stability. Light traveling through the ice bends at different angles, creating shimmering bands of brightness across the lake bed. In some places, methane bubbles freeze into stacked white disks, creating surreal patterns that contrast beautifully with the clarity around them. These frozen lakes become natural observatories, showcasing an underwater world that is hidden during every other season. Snow lines sweeping across mountains provide a visible map of wind currents, showing how air flows over ridges, valleys, and exposed rock. Ridges that face prevailing winds often remain bare, while sheltered slopes accumulate deep drifts. Thin ribbons of snow sometimes form along contour lines where the wind loses just enough momentum for snowflakes to settle. In high, narrow passes, wind may carve snow into elongated formations that match the direction of reduced turbulence. Mountaineers use these patterns to judge avalanche risks, since uneven loading and wind-carved formations indicate areas where snow is unstable. Over time, storm after storm reshapes these patterns, creating evolving maps of winter airflow etched in white across the rugged terrain, each one documenting the unique combination of wind strength, direction, and duration that produced it. Winter storms over oceans create dramatic effects beneath the surface as well. Strong winds churn the upper layers, mixing warm water with deeper cold water and disrupting the stratification that forms during calmer months. This turbulence can create temporary pathways that transport heat, nutrients, and salt across different depths. Nutrients lifted from the deep layers can spark short-lived blooms of biological activity when sunlight returns. Storms may redirect or weaken major surface currents, altering the movement of water masses for days or even weeks. After the storm passes, the ocean does not immediately return to its previous state. Instead, the layers slowly rebuild themselves as temperature and salinity differences re-establish their usual patterns. Marine organisms respond quickly to these changes, adjusting feeding, movement, and reproduction in response to the shifting environment. Ice crystals also form intricate structures far more delicate than simple sheets under certain temperature and humidity conditions. Water vapor may assemble into branching crystalline feathers or fans on cold surfaces. Each branch extends outward, splitting into smaller blades as the crystal grows, guided by minuscule variations in temperature and air flow. These frost feathers appear on windows, stones, or metal surfaces, each one unique, shaped by the specific conditions of its formation. The resulting patterns often resemble leaves, trees, or ferns, even though their formation depends solely on molecular arrangement and environmental conditions. These fragile structures highlight winter's ability to create natural art that changes from moment to moment. Winter conditions also reshape communication among animals. Cold, dense air carries sound differently than warm air, allowing deeper or slower calls to travel farther. Many species adjust the pitch or timing of their calls to compensate for snow's tendency to absorb higher frequencies. Frozen forests, with their rigid branches, transmit vibrations differently than leafy summer canopies, altering how animals detect danger or locate companions. Scent-based communication changes as well, because cold air preserves chemical signals that would disperse rapidly in warm weather. Tracks in snow, heat signatures, and compressed scents all combine to create an environment rich with cues that animals interpret and adapt to throughout the season. Snow cover also influences nearby urban climates by altering how heat is absorbed and released. A thick layer of snow reflects sunlight that would otherwise warm the ground or surrounding buildings. As a result, both daylight temperatures and nighttime heat release patterns shift. Cold air flowing from snow-covered fields can drift into cities, lowering local temperatures and influencing wind patterns. Snow reduces the amount of heat that urban surfaces store, which can temporarily weaken or flatten the urban heat island effect, narrowing the temperature difference between cities and rural surroundings. This seasonal transformation demonstrates how winter's reach extends deep into urban environments, shaping energy balance and modifying the rhythms of daily life. All of these interactions, between cold air and warm ground, between ice and rock, between wind and snow, between oceans and atmosphere, combine to show that winter is not a static season of simple dormancy but a period of extraordinary activity, complexity, and transformation. Beneath its stillness lies a world constantly reshaped by physics, chemistry, biology, and climate, where processes big and small interact to reveal structures that are hidden in warmer months and to reshape the world in ways both subtle and profound. Winter reveals the invisible, preserves the ancient, amplifies the distant, sculpts the landscape, alters ecosystems, and continually rewrites the environment through its powerful and ever-active forces. Snow-filled parks, fields, and riverbanks become cool zones that influence air circulation on a neighborhood scale, acting as temporary climate modifiers that shift the balance of warmth and cold across urban areas in ways that would be impossible during other seasons. And as the snow melts, the release of moisture further alters these delicate local conditions by adding humidity to the air, changing ground temperature, and affecting how heat radiates from various surfaces. Urban planners and meteorologists carefully monitor these interactions to understand how winter landscapes reshape city climates, noting how snow does not merely sit at the edges of cities but becomes part of the complex temperature system that affects everything from energy use to daily weather patterns. And this interplay between frozen surfaces, cold air, built structures, and the slow transition towards spring reveals how even a thin blanket of snow can reshape the thermal balance of a region. Frozen air, especially during extreme cold spells, can create visible shock waves around moving objects, and when temperatures drop far below freezing, the air becomes so dense that sudden movements compress it into visible patterns, allowing fast-moving objects such as birds, vehicles, or even thrown snowballs to generate faint lines or puffs of condensed moisture where air pressure changes abruptly. These shock patterns appear because cold air holds very little water vapor, so even tiny shifts in temperature or pressure can force that vapor to condense for just a moment before dissipating, producing white outlines or small bursts of mist that seem to trace the motion of anything that cuts through the frigid air. In extremely cold regions, people may see this effect when exhaling forcefully, throwing boiling water into the air, swinging an object rapidly, or even snapping a cloth, each event demonstrating how sharply cold air responds to motion and how winter reveals physical behaviors of the atmosphere that remain hidden during warmer seasons. Winter fog, too, becomes a laboratory for unique transformations, sometimes becoming so cold that it forms ice crystals midair. Under certain conditions, tiny droplets within fog remain supercooled, staying liquid even though temperatures are well below freezing, and when these droplets encounter dust particles, snowflakes, or even gentle disturbances, they can freeze instantly, transforming the fog into a floating field of ice crystals that sparkle as they drift through the air. Unlike snowflakes formed high in the atmosphere, these crystals originate close to the ground and fall slowly, creating a shimmering curtain that moves with the breeze, and the transformation can occur suddenly, turning ordinary fog into an icy display that looks almost otherworldly. These crystals often collect on exposed surfaces, forming delicate frost that grows in the direction of the wind, and the event demonstrates how sensitive supercooled droplets are to subtle environmental changes, making winter fog a stage for rapid freezing processes that reveal the fine boundary between liquid and solid in the natural world. Frozen ocean waves also become witnesses to winter's power, storing energy that releases when thawed. In polar regions, waves continue to move beneath the surface even as the upper layer freezes, and when temperatures drop fast enough, the tops of these moving waves solidify into curved ridges that preserve the shape of motion below. These frozen waves record patterns of force that were present at the moment the surface froze. The ice flexes slightly with continued movement of the water underneath, storing mechanical stress just as a bent branch stores tension, and when sunlight returns and the ice begins to soften, these stresses release as cracks, pops, and subtle shifts across the frozen surface. In some cases, the thaw reveals hidden ridges that collapse suddenly, creating short-lived jolts that ripple across weakening ice sheets, and researchers study these frozen wave structures to understand how sea ice responds to winter storms, ocean circulation, and long-term climatic change. Frozen waves thus become records of past motion and future instability, showing how closely connected ice is to the water that shapes it. Winter skies can generate extremely rare atmospheric arcs that few people ever witness. On the coldest days, tiny ice crystals suspended in the air interact with sunlight to create arcs far more complex than ordinary halos. These crystals often take the form of flat plates or slender columns that drift into gentle alignment, allowing light to bend through them in predictable but intricate ways. When conditions are perfect, almost impossibly perfect, multiple arcs appear at once, forming loops, curves, pillars, or split bands at unusual angles across the sky, and each pattern depends on the orientation of the crystals and the angle of the sun. Some arcs appear only when the sun is extremely low, while others flash briefly as the sun climbs or descends through a narrow range of elevation. Their colors can range from faint white to subtle reds and blues or even strong, glowing hues that resemble ribbons of delicate light. Scientists classify these arcs by analyzing the geometry of the crystals that create them, but most people never see these displays because they require air that is extremely cold, extremely clear, and filled with just the right type of ice crystals. For those fortunate enough to witness them, the winter sky becomes a complex optical instrument, projecting patterns created entirely by the frozen air itself. Snow depth can determine where entire species migrate, making it one of the most influential winter factors shaping animal movement across continents. Animals that travel long distances rely on environmental cues to choose safe and productive routes, and snow thickness is one of the most important of these cues. Deep snow slows movement, hides vegetation, and increases energy expenditure for both herbivores and carnivores, so many species adjust their migration paths based on where snow accumulates. Caribou, for example, avoid regions with deep powder because it restricts access to the lichen they rely on. Predators track these changes as well, shifting their hunting routes to follow prey. Birds that feed on seeds or insects avoid areas where snow is too thick for ground foraging, while small mammals alter their paths to seek regions with snow that is either shallow enough to travel through or deep enough to burrow beneath for insulation. Long-term climate shifts change snow depth patterns across continents, which in turn reshape migration corridors, demonstrating how snow acts as a moving map that guides animals towards survival year after year. Frozen ground beneath the snow can shape rivers long before spring thaw, influencing water flow in ways that become visible only once temperatures rise. When winter temperatures fall, moisture in the soil freezes and expands, altering the structure of the ground and creating subtle but important rises and shifts that redirect the movement of surface water. This expansion can raise patches of soil, divert small streams, or change the channels that meltwater will eventually follow. During winter, streams may shift sideways as frozen soil blocks their usual paths. Ice can anchor fallen branches or debris that accumulate into temporary natural dams, shaping the distribution of water beneath snow layers and guiding it into new routes. Ice can anchor fallen branches or debris that accumulate into temporary natural dams, shaping the distribution of water beneath snow layers and guiding it into new routes. By the time spring arrives, the meltwater follows pathways that winter has already engineered. Frozen soil also changes erosion patterns because hard ground resists water flow early in the season, causing streams to cut deeper into areas that thaw sooner, altering channel depth and shape from year to year. Together, all of these winter phenomena, snow-cooled cities, visible shock waves in frozen air, supercooled fog that transforms into falling crystals, frozen waves that store the memory of motion, atmospheric arcs that turn the sky into a prism, migration routes redirected by snow depth, and rivers reshaped by frozen ground, reveal the astonishing power winter has to sculpt landscapes, influence ecosystems, modify the atmosphere, and uncover natural processes that remain hidden during every other season. Winter is not merely a dormant period of cold and stillness. It is a dynamic stage where the world reorganizes itself, exposing the delicate interactions between air, water, temperature, structure, and life. Though many of these transformations unfold quietly or invisibly, each contributes to the ever-changing system that shapes our planet. Over many years, the repeated effects of winter subtly but relentlessly reshape the landscape, carving, pressing, shifting, and sculpting the ground in ways that are easy to overlook when everything appears quiet and frozen, yet these small seasonal forces accumulate into dramatic long-term changes that permanently alter riverbeds, valleys, slopes, and entire watersheds, preparing the shape of future waterways long before the ice melts and the spring floods arrive, because even in the deepest cold the ground is continuously responding to the pressure of snow, the expansion of ice, and the movements of frozen layers beneath the surface. Winter storms, although they may pass in a matter of hours, leave behind patterns that map their path with remarkable clarity for anyone who knows how to interpret them, and after a major system sweeps across a landscape, the distribution of snow often carries a visible imprint of the storm's internal dynamics. Bands of heavy, sculpted snowfall show regions where strong upward motion occurred, while lighter, powdery zones reveal where lifting was weaker and precipitation fell more gently. As winds wrap around the core of a storm, they sculpt snowdrifts into curves and ridges that align with the flow of air near the surface, revealing details about wind speed, direction, and turbulence at specific moments during the event. Icy ridges, packed layers, and sharp contours show where the storm paused, shifted direction, or intensified. Even melt patterns that appear shortly after the storm passed provide clues, indicating which areas received brief pulses of warmer air or direct sunlight through gaps in cloud cover, and meteorologists use these signatures to reconstruct the movement of storms in regions where direct measurements are sparse. Nature, in this way, becomes a large archive of atmospheric behavior, recording the path of each winter system in the shapes, layers, and textures it leaves behind on the ground, and though the storm itself may vanish quickly, its imprint remains visible to anyone trained to read the clues etched into the landscape. Ice offers another kind of record, forming double layers with distinct properties whenever water freezes in stages. The first layer usually develops under calm conditions and tends to be clear because impurities have time to settle toward the bottom, while a second layer may form later as temperatures fluctuate, resulting in trapped bubbles, scattered impurities, or uneven crystal growth that gives the upper layer a more opaque or frosted appearance. These layers bond together yet retain unique characteristics, with the lower layer often strong enough to support significant weight, while the upper one remains fragile and prone to cracking. In lakes and ponds, differences in clarity, density, and crystalline structure affect how cracks propagate, how the ice flexes under pressure, and even how sound travels across the surface. Because sunlight penetrates each layer differently and temperature shifts cause them to expand or contract at different rates, producing faint popping sounds or subtle movements as stresses equalize. The existence of double-layered ice offers insights into the weather history of a region, recording quiet nights, windy episodes, abrupt freezes, and gradual cooling events in thin, translucent strata that preserve detailed evidence of past conditions. In volcanic regions, winter adds another layer of complexity. Because snow blankets can trap volcanic gases that normally escape through vents, fissures, and porous ground, deep snow acts like an insulating dome that prevents gases from dispersing freely into the atmosphere, allowing them instead to accumulate in pockets with distinct chemical compositions. When warmer weather arrives or sunlight softens the surface, these gases release in sudden pulses, carrying with them crucial information about conditions deep below the Earth's surface. Snow can also filter and capture mineral particles from the gases, leaving behind bright mineral deposits once the snow melts. And in places where heat from rising gases is strong enough, small tunnels form upward through the snowpack, creating vents that resemble tiny chimneys, clear signs that the ground below remains active even during the coldest months. Thus, snow does not silence volcanic activity. It simply hides it, preserving chemical clues in layers that only reveal themselves when conditions shift. Frozen lakes, meanwhile, transform into vast resonant surfaces that can transmit and amplify vibrations over astonishing distances. A single forceful impact can send ripples of sound traveling outward across the ice, maintaining energy efficiently because the frozen sheet acts like a continuous, rigid membrane. People standing on such lakes often hear cracks, shifts, or even distant footsteps echoing across the surface with surprising clarity, because the underlying water helps reflect and reinforce sound waves, creating an acoustic environment unlike any other season. These unique acoustic properties allow researchers to study ice thickness, stress distribution, water movement beneath the surface, and even the early stages of freeze-thaw cycles by analyzing how vibrations travel across the frozen expanse. Winter also affects the natural world through atmospheric pressure changes, which can dramatically alter animal behavior. Many species sense fluctuations in pressure long before humans notice them. Birds may change feeding patterns as falling pressure signals an approaching storm. Mammals often seek shelter earlier than usual when rapid pressure drops occur, and fish adjust their depth depending on how buoyancy is affected by pressure differences. Even insects that remain active through winter instinctively modify hiding or feeding strategies to avoid exposure to turbulent weather, and domestic animals frequently display subtle but consistent shifts in energy or movement when pressure changes sharply. These behaviors are adaptive traits developed over long evolutionary histories because pressure variations offer valuable early warnings of changing weather, especially during winter when storms tend to be more intense and frequent, making animal behavior a living indicator of approaching atmospheric shifts. Winter's cold also transforms the physical properties of organic materials such as wood. As water inside the wood fibers freezes, the material stiffens dramatically, causing flexible cell walls to lose moisture and torque into rigid structures that resist bending. A branch that bends easily in summer may snap sharply in winter, and wooden structures such as fences or beams often produce loud, ringing sounds when temperatures drop rapidly because the sudden contraction generates internal stress. Collisions that would produce dull thuds during warm months instead yield crisp, metallic tones during extreme cold, revealing how deeply temperature influences the acoustic and structural qualities of wood. Furniture, tools, and buildings constructed from wood must account for these seasonal shifts, and winter reveals both the hidden strength and the brittle vulnerability that emerge when organic material transitions into a near-metallic state under freezing conditions. Similarly, the cold can lock minerals into place in ways summer never can. When temperatures plunge far below freezing, water within soil and rock pores turns to ice, expanding and pushing mineral grains tightly together. This freezing cements loose particles, stabilizing them in arrangements that would typically shift under milder conditions. Furniture, tools, and buildings constructed from wood must account for these seasonal shifts, and winter reveals both the hidden strength and the brittle vulnerability that emerge when organic material transitions into a near-metallic state under freezing conditions. Similarly, the cold can lock minerals into place in ways summer never can. When temperatures plunge far below freezing, water within soil and rock pores turns to ice, expanding and pushing mineral grains tightly together. This freezing cements loose particles, stabilizing them in arrangements that would typically shift under milder conditions. Fine-grained sediments such as clay and silt become rigid structures resistant to erosion, and rocky terrain develops interlocking ice bridges between grains that temporarily strengthen the stone. This natural freezing process can preserve delicate mineral formations or fossil structures that would crumble in warmer weather, and researchers studying frozen ground often discover minerals caught mid-transformation, held in suspended chemical states that reveal details about the slow geological processes unfolding within the Earth. When spring arrives, these frozen relationships loosen and the structure weakens again, but winter offers a brief moment of geological stillness, a snapshot of Earth's interior processes frozen in place. Even the rate of snowfall responds dramatically to subtle temperature changes. When temperatures hover just below freezing, the atmosphere becomes extraordinarily sensitive to small fluctuations. A drop of just 1 or 2 degrees can alter the shape, growth rate, and clustering behavior of snow crystals, influencing how they accumulate on the ground. Slight cooling increases the amount of moisture the air can convert into ice, allowing snowflakes to grow more quickly, and these small changes determine whether crystals merge into large, fluffy flakes that fall rapidly and accumulate quickly or whether they form tiny grains that drift slowly and pile up more gradually. Storm systems respond sharply to these microscopic shifts. Clouds that are only slightly warmer may produce light, delicate flurries, while clouds that cool just a bit more can generate intense bursts of heavy snowfall. Winter, in all of these interconnected phenomena, shows how small differences in temperature, pressure, moisture, and structure can produce vast variations in landscape, atmosphere, sound, geology, and living behavior, proving that the frozen world is never truly still but instead filled with subtle, continuous motion that shapes the Earth in ways both visible and hidden. Winter storms can push snow high into mountain passes even without the presence of wind, creating a striking and often misunderstood phenomenon where strong vertical air currents, rather than horizontal gusts, become the primary force shaping the landscape. In some intense winter systems, moist air rises rapidly over rugged terrain, cooling as it ascends and condensing into thick, heavy bands of snow that accumulate in high passes, saddles, and narrow mountain corridors. This upward transport of snow contrasts deeply with the more familiar image of wind-driven drifts and blizzards. Instead of being blown sideways, the snow is carried gently but powerfully upward, lifted by buoyant air that has been warmed slightly before rising and then chilled sharply in the higher elevations. The interaction between warm, moisture-rich air masses and cold mountain air creates a dramatic vertical conveyor belt of frozen crystals, depositing deep layers of snow in locations where a casual observer might assume calm or uneventful conditions. Mountaineers and hikers often discover unexpectedly deep snowdrifts in high-altitude shelters, bowls, and passes where the surface winds never stirred, evidence of the hidden and complex dynamics of winter storms. These upward-driven snow patterns become a kind of weather map etched across the peaks, revealing areas where air currents surged, slowed, spiraled, or cooled, telling a quiet but detailed story about the storm's internal structure and how the atmosphere sculpted the terrain in ways that surface-level observations alone could never predict. At the same time, Frozen lakes become vast natural canvases where stress, cold, and contraction work together to produce astonishing geometric crack patterns. When a lake freezes with uniform thickness and consistency, the surface behaves like a rigid sheet, and as temperatures drop further, the ice contracts, building tension that must be released through fractures. Instead of random or chaotic shattering, the cracks spread along clean geometric lines, often forming long straight paths, intersecting stars, branching fans, or triangular grids. These patterns emerge because stress concentrates at symmetrical points across the ice sheet, and as fractures propagate, they follow the mechanical logic of a material behaving like a uniform plate. Sunlight reflecting off these cracks reveals sharp, almost perfect edges that contrast against the smooth surrounding surface, and the sounds created during the cracking process echo like eerie, resonant booms across the frozen lake, sometimes traveling miles across the silent winter air. Each geometric network of cracks represents a moment of tension release, a snapshot of the lake adjusting to changes in temperature, pressure, and underlying water movement. Scientists study these fracture patterns to evaluate ice strength and thickness, but to the eye of a winter traveler, they appear almost artistic, as though the lake itself has expressed its quiet tension in an intricate frozen design. As these icy landscapes shift, winter conditions beneath the soil shape the survival of seeds locked underground in dormancy. Beneath snowdrifts and frozen earth, countless seeds lie waiting, their biological clocks slowed to near stillness as winter determines which of them will awaken when warmth returns. Some seeds require long exposure to cold to trigger biochemical changes, known as stratification, that prepare them for spring germination. Others depend on the insulating blanket of snow to protect them from rapid freeze-thaw cycles that could rupture their delicate outer coats. Moisture trapped in frozen soil preserves seeds by preventing rot during months of inactivity, while the rhythmic expansion and contraction of freezing ground can carry seeds deeper into the earth or pull them closer to the surface depending on the microclimate. Slight variations in soil temperature across valleys, hillsides, and shaded forest floors create numerous tiny survival zones where certain species endure better than others. Through these subtle and powerful forces, winter acts as a natural gardener, selecting, preserving, and preparing the seeds that will populate the landscape once the thaw arrives. In another surprising twist of winter physics, ice itself can become a magnifying lens capable of igniting small fires when the sun returns. Under ideal conditions, when water freezes without air bubbles, sediment, or impurities, it forms exceptionally clear, curved ice shapes. These curves can focus sunlight into an intense point of heat much like a magnifying glass. During late winter or early spring, when the sun's angle becomes stronger, these naturally formed ice lenses can concentrate sunlight onto dry vegetation, raising temperatures enough to spark small patches of fire. Though rare, such fire-starting ice has been documented in regions where large, transparent ice formations catch direct sunlight. It is a reminder that winter's cold tools can create unexpected interactions with light, turning frozen water into an optical instrument capable of shaping the environment in ways few imagine. Meanwhile, cold winter air becomes a powerful diagnostic lens for revealing hidden heat sources and structural weaknesses in both natural landscapes and human-made buildings. When temperatures plunge, the stark contrast between warm interior spaces and freezing exterior air causes heat leaks to stand out dramatically under thermal imaging. Warm patches around windows, doors, rooftops, and poorly insulated walls glow brightly against the cold background, allowing builders, surveyors, and homeowners to pinpoint inefficiencies that remain invisible during warmer seasons. The same principle applies on natural terrain. Geothermal springs, decomposing plant matter, and burrowing animals generate subtle warmth that becomes glaringly obvious against frozen surroundings. Winter simplifies the thermal landscape by lowering overall background temperatures, allowing even small anomalies to stand out with extraordinary clarity. This makes the cold season one of the most revealing periods for studying both energy flow in buildings and hidden biological or geological processes in nature. Deep snow also transforms the sensory world of predators and prey by burying scent trails that animals rely on during warmer months. When snow falls thickly, it seals scent markers beneath its surface, muffling or eliminating the chemical traces left behind by animals. Predators that depend on smell must adapt quickly, shifting to new strategies such as listening for movement under the snow, watching for visible tracks, or positioning themselves near choke points where prey is likely to pass. Prey animals, in turn, take advantage of reduced scent detection to move more freely or explore new routes. The entire ecosystem adjusts, with each species rewriting its survival strategy to fit the sensory limitations imposed by winter's frozen blanket. Beneath the ice, water itself behaves in a way that protects aquatic life through the coldest months. As water cools, it becomes denser until it reaches a point just above freezing. Below that, its density decreases, causing the coldest water to float. This unusual behavior creates a stable layering system in lakes and ponds where slightly warmer water remains insulated at the bottom while ice forms above. The ice layer protects the liquid water underneath by preventing deeper layers from losing heat too quickly or freezing solid. Fish, amphibians, and microorganisms survive in this cold but life-sustaining refuge where oxygen moves slowly and energy needs remain low. Without this strange density property, winter would freeze entire bodies of water solid, wiping out aquatic ecosystems each year. High in the atmosphere, winter also produces frozen clouds that drift silently across the sky, containing countless tiny ice crystals suspended in air so cold and stable that the crystals remain afloat instead of falling as snow. These clouds can persist for long periods when gentle upward air currents balance the pull of gravity. They reflect sunlight sharply, brightening winter days, and trap heat from below during long nights, playing an important role in regulating seasonal temperatures. Only when humidity, temperature, and atmospheric motion shift in very specific ways do the crystals grow large enough to fall as snow. Until then, they drift silently through the upper atmosphere, shaping winter's light without ever touching the ground. And finally, as the last quiet days of winter settle into your thoughts, the season begins to fade into something soft and distant, a blend of cold air, hidden motion beneath frozen surfaces, and quiet changes inside snowpack and ice layers. All these intricate processes slip into the background like a landscape dissolving into twilight, leaving behind a sense of calm, silence, and gentle stillness. Winter carries with it a quiet clarity, a slow unspooling of subtle movements and transformations that continue with or without our attention. As your mind drifts across these winter scenes, upward moving snow and silent mountain passes, geometric cracks stretching across frozen lakes, seeds waiting in dark soil, heat leaks glowing in frosty air, predators adapting to snow-smothered scent, ice lenses focusing sunlight into unexpected fire, drifting frozen clouds glinting above, you may feel the season settle around you like a soft blanket. There is nothing to chase and nothing to solve, only the slow, patient rhythm of winter shaping the world in ways both visible and hidden. And as you reach the end of this quiet journey, the night feels wide and calm, the world simple again, and you are free to drift at your own pace, without weight, without urgency, carrying with you only the gentle stillness winter leaves behind.